example. Let's see. Okay. All right. So recording has started, and let's see if I can get, trying to remember where where I had stored your your the files that I was working with you all. I think it's in not in my Dropbox. I think it's in my this folder here, but I'm trying to remember what for 6 notes. Linked list. Okay. Linked list first and linked list creation. Okay, so we had reached a point where we got to some code where we created the linked list. And what we did is that, hold on. Okay, so what did we do so far? Basically, we defined the node, and our node was simple. We created this struct, and this struct is the blueprint for our node. And what our node had was a part that could hold a name. So this part can hold a name as some sort of data. And this here was the pointer to the next node. And so what we did is that we created a pointer to the head node. So this is just a blueprint. This is a concept. This, when we say create a node, is what is going to be reserved in memory. Okay? So once we have this concept here as the struct, we created a pointer called head, and head is pointing to null right now. Right? Head is pointing to null right now. And then we created a pointer called current, or cur, and cur is also pointing to null right now. And what we did here after was that we said, okay, see right now. All right. So we have head, we have null, we have main. So we start and we create a temporary array string to hold the name. And we have an integer called stop, right? And this will allow us to stop taking names. And what we did was that we said, okay, please enter a name. And as long as the name is not the word stop, as long as the name is not the word stop, the first thing that we do is we check to see if the head node is null. And if the head node is null, which it is in this instance, we create the first node and let head point to that node. So what happens in this instance? What happens in this instance is that we have head, that same variable head that we pointed to, and we use this line here, struct node malloc size of node, and we will allow for this node to be created here. And head is going to point to this created node. We also would let cur point to this created node as well. Then we say car dash next is equal to null. So we say that, okay, this node will point to null. So if it is that we have to traverse from head to the end, this is a node of 1. Okay, this is a node of 1. So there's only one node in this list. And we store whatever name we entered inside of here. So if our name was Jane, we store Jane inside of there. Okay? That's what this last line did here. So we go down, and of course, once we go down, we have to skip over the else, because we did the code that was associated with the first node, and because we were inside of this first else as well, we skip over this part that would give us the condition to stop the loop. So then we come back around and we say, please enter another name, right? Or enter a name again. We get that name and store it in the temp variable. So let's say we enter Jim this time. Let's say we enter Jim this time. And if Jim was equal to stop, we would have gone and go to the stop condition, but Jim is not the same as stop. So this condition inside of this if statement is true. And the thing is, the head node is not null, because the head node points to the address of the first node. Okay, so what do we do now? We will do what's inside of the else. So what is the else condition going to do? The else condition is going to say create a new node and make the next pointer of the current node, which is the last created node. So car, the purpose of car is to be the last created node. And what we say is that the current node, right, dash next, should hold the address of this newly created, or point to the address of this newly created node that we have. Okay, so we just created a node here. That's what this line is saying right here. We just created a node that allow for car dash next to point to it. And then what we say is to make this newly created node current, which is what I just said car is. Car is always the most recently created node. And now what we want for this node is for this node to point to null, because this is the inside of the linked list. And then we say copy the name Jim into this node that was recently created. The stop condition is not anything besides 0, so this while condition holds true. We go again. We could create one more name, okay, just to see it through. Again, what would happen is that this current node is going to point to the newly created node, right? We could put the name Anna in, sorry, no, we're going in order. I jump in the gun. All right, so we're not putting Anna inside there just yet. We are going to say car is equal to car dash next. So car is now going to be equal to this newly created node. We say car dash next is equal to null. So we put this node to point at null, and then we copy the name Anna into this newly created node. And then let's go around. We haven't stopped yet. Let's say, for instance, the name that we've put in is stop. Right, the name that we put in is stop. And what would happen is that stop would give a value of 0 when you compare it to stop using string compare I. So the value for the stop condition will switch to 1, and then we will stop the loop. Hold a second, please. Yes. So we've reached the point where we stop, we break out of this loop here, and this is the linked list that we've created. Any questions so far? Anybody? Any questions so far? All right.
No, sir. No.
All right, good. And so in order to traverse this linked list, which means to run the linked list from the beginning to the end, right? In order to traverse this linked list, we are going to have to reset where cur is, because cur has to start over from head and run until cur is equal to null. So to print out the data, the first thing that we have to do is reset the position of cur. So we reset the position of cur to the same position that head is at. So we put cur back to here, okay? And then we said, all right, print out what cur dash name is, and then make cur point to the next position. Print out what cur is, and make cur the next position. Print out what cur is, make cur the next position. And then we can't go any further because this loop continued only while cur is equal to null, but eventually cur becomes null. So that's why we're able to traverse this linked list in such that manner. Everybody understand? Does everybody understand? Is everybody good with this? Getting no messages and getting no
Yes, sir.
Yes, sir.
All right.
Right.
Good, good. Anybody have any questions on it? So if we were to run it, okay. I just want to see something here. Struct node pointer. Is it that? Okay. I was supposed to take a look at that that warning the other day, but it had worked with the warning. It was just that something was going on with it. So we enter the name. So we have our prompt to enter the name, and we could enter a couple names here. All right. These my daughter's names. C-A-H-A-R-A, Zahara, Y-E-J-I-D-E, H-D. We enter Valdez, and then we enter the word stop. And so what happens is that we get exactly what we put into this structure, this dynamic memory structure, which will grow to whatever size we want it to be, as long as we have the appropriate memory to hold on to it. All right, so we have them printing back out down here. Any questions about that? No. So we're good to go. All right. All right. So that was just a recap of the linked list. And since everybody is comfortable with the linked list right now, the next thing that we want to talk about is the concept of stacks and queues. Okay. So I'm going to share my screen again, and we're going to talk about stacks and queues. So, which one we want to start with, stacks or queues? Alicia said stacks. I barely heard what. Yes, no?
Yeah.
All right. All right. Alicia sounds like she's a little far from the microphone, but I heard yes. All right. So we start. And what is a stack? All right. What is a stack? And I mentioned before is an abstract data type. An abstract data type. And just to recap the concept of an abstract data type, an abstract data type is a structure that has associated behaviors and rules for interacting with it, such as adding information and retrieving information. So an abstract data type is a structure that holds data and has behaviors associated with the removal, let me move the word stack here, with the removal, or let me say the addition, and removal of data on a variable associated / created in that type. Okay, so an abstract data type has specific rules that govern how that data type definition so different with what, Alicia?
I realized that like for ADTs, everybody has a definition for it.
Like a different definition. Because again, because you see that word abstract, right? Abstract is it means that, you know, it's a kind of difficult-ish concept. It's not difficult in that the rules are the same. The abstract data type just simply means that it's essentially created, and you also have created behaviors that go along with the data type. So I wouldn't say that it's very different in terms of everybody's definition of it. It's just that, you know, it is what it is. Hold 1 second again, please. Yeah, sorry about that. Finish a little test. So she is done, but I'm trying to tell her look over the work now. Like, you guys should look over your work when you are finished with your test as well. You know, because that you guys do that, right? Right?
Yes.
Sometimes.
I know. I can't fault you all because sometimes I I don't do that. I don't do that all the time as well. It depends on how the test is going. So like if the test is like really hard and I just wanted to get out, sometimes it's just like, you know what? It is what it is on the paper, and that's it. Hold on. Yes, EG.
So what kind of talk is that? So you're supposed to be encouraging us better. So
I know, but I'm being open and honest with you all. Right? I'm not saying do as I do. I'm just saying sometimes you want to, yeah, sometimes that second guessing is pain. Like, you know how much times I walk out of an exam knowing that I had the correct thing and then I changed it at the last point and everybody else outside the exam talking about a hard question and it's like, nah, for sure the answer is that first thing that you had down and then you want to cry because you know you changed it. Right? So yeah. See, at least you know the pain. Right? But we did well. You all did well. Right? Sometimes it works out for me, sometimes it does not work out for me. But you all generally did well. So no worries about it. All right. Let me just ask before I continue. Clay, you got through with everything?
Yes, I done sent off.
All right then, cool. All right, so we're going back to the abstract data type. So let's work with this. Your abstract data type has those behaviors or functions associated with essentially the way that you manipulate the data in your data type. Okay, so we want to talk about stacks. And to talk about stacks, all right, you would think I don't know anything about stacks, right? Being a teacher, because teachers don't make a lot of money, all right? When you talk about stacks, maybe teachers only know about stacks of paper, not like not like good people, but like exam papers, all right? But I wouldn't know about any other types stacks of papers. All right, what is a stack? Anybody could tell me what a stack is? Like when you hear the word stack, what do you think about?
so like obviously with the money, like obviously a bunch of things, I don't know, you stack like pressed up one on top of each other.
Yes, that is a stack, right? So we have a lot of stacks that we interact with in life. Okay, we have like normally when you put plates in your cupboard, you put it in a stack. You have plates stacked on top of each other. Of course we know, as I said, it have like stacks of paper. Okay, so a stack is a data type. It is that simple. It is that simple. It's exactly what it is. It's a stack. All right. So when we're talking about stacks, we're actually talking about a data type that is visualized like this. Okay. A data type that's visualized like this. So if we define a stack, we have essentially a top of the stack and you take data off at the top of the stack. So it's a data type where the rule is, right? It's a data type where the rule is that you can only add data and remove data from the top of the stack. From the top of the stack. Okay? So you could only remove data and add data from the top of the stack. So where is the top? There's only one side from which you can add information to the stack. There's only one side that you could remove information from the stack. So as I said before, if I have my stack right here and my stack is empty, I could think of a stack as an array on its side, and because of that, we have our indices. 3, 4, 5, 6, 7. If my stack is empty, then the value for the top is going to be -1. Is minus one a position that I can access in my array? Is that a position that I can access in my array? No, it's not. So if the top of my stack is -1, then it means my stack is empty. If I want to add values to the stack, it's called pushing values onto the stack. So to add values to the stack, we push values onto the stack. So if it is that I this command, push 10, push 5, push 200, and then push 40. In this order, what is going to happen is that I'm going to have the value of 10 pushed onto the stack. So if I do this push 10, my value of 10 will go here, and the value associated with top will move to 0. The value 5 will go here, and the value associated with top will go to 1. If I push 200, right, 200 is going to go here, and the value associated with top will move to, oops. The value associated with top, why did this ungroup? Oops. Right. We'll go to here. Just give me a second and let me sort this thing back out. Right. 200 will go to here. And then if I push 40, 40 will go to here, and the value associated with top will go to here. So to add values to this stack, we push values onto the stack. The values always come in. Once we push, it goes on to the top of the stack. Okay, because when we have a stack, to add things to a stack, we always put it on top. That is the nature of stacking. Agreed? Are you with me, my students?
Yes, sir.
Right. It's not a hard concept at all. This is really easy. The hardest part is representing it as an algorithm, and I know that you are all professionals in terms of being students and understanding and creating these programs. So I'm not worried about that either. But the concepts behind them are super easy. All right. And then we can continue and say to remove values from the stack, we pop. Okay, so to remove values from the stack, to remove values from the stack, we pop a value. Okay, we pop a value from the stack. So we call the function pop. We call the function pop. And that function pop allows us to remove a value from the stack. So if I had this same stack that had some values in it, okay? If undo. Wow. Right. So if I had this value, sorry, the same stack, which have these values in them. All right. And I want to now remove some values from this stack. What am I going to do? I'm going to, if I pop, right? So if I say pop, 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 right? And I say value 1 is equal to pop, value 2 is equal to pop, and value 3 is equal to pop. And now I have these variables, value 1, value 2, and value 3. Okay? When I call value 1 and I pop the value from value 1, the pop operation takes a value from the top of the stack. So when I call that first value 1 pop, and I say value 1 is equal to pop, I'll be taking the value of 40 out of the stack. I'll be taking the value of 40 out of the stack, and I'll be moving the top down to the previous value. Same thing for value 2. If I take the value 2 out of the stack, I'll be taking the value 200. I'll be removing 200 from the stack, and I'll be carrying top down to the previous value. Value 3, if I pop it, I have the value of 5 being stored in value 3. I remove the value of 5 from my stack, and the value of top goes down to 0. And that's popping a value from the stack. It's as simple as this, people. You can't make it more than that. Any questions about stack and stack operations so far?
Joshua, Hannah.
Yes, Joshua.
So you can only pop the top value.
Only from the top value.
So if you want to access another value in the stack, then you have
to pop all the other values above and above it, and then probably put it back into the stack.
Yes.
Right? So a stack has a specific characteristic. A stack is known as a last in, first out structure. Right? So a stack, so it's something to note. A stack is a last in, first out structure. As in, the last value that you placed into the stack is the first value that you will get out of the stack. Understood? All right. So I'm going to take a little break here for actual break. And so I'll pause the recording, and then we'll resume the recording after the break. Okay? So we're going to take a little break. Recording is okay, so we're back on. We kind of just went through the general concepts of structs, right? And of course, we kind of went over what an ADT is. So we want to go through what a queue is, all right? Queues. So what is a queue? Anybody? Kalika. Let me see if I could hear Kalika's voice today. Kalika, you there?
Yes, sir, I'm here.
All right. What is a queue? When you hear the word queue, what do you think about?
So I think about a line of things.
Correct. Okay. So we have a queue, and a queue is a line. Kalika is correct. It's a line. It's just a data structure that mimics what a line, a line is, right? So a queue, essentially, any line has a front and a rear. So a queue is a data structure. And again, we have our indices 0, 1, 2, 3, 4, 5, 6, 7, 8. And the queue has a front, which typically is always this first position. And if the line is empty, then the rear of the line is going to be at a position that doesn't exist. Because if the line is empty, then there's nobody in the line. So that queue, that front position doesn't really move in a standard queue. But the rear position does move. Okay? So if it is that somebody joins the line, then the front and the rear is going to be the first position. And if people keep joining the line, then the rear of the line is going to move back. Okay? So a queue, let's just define a queue. A queue, right? And the queue is such a weird word because, I mean, you have like 4 letters that you don't really need to spell the word queue, right? But then if it is that if you take out the last 2, you have a K, which is kind of weird. So why is it that these extra letters, Q, gives it the same letter, the same sound as just the single letter, but the 3 letters? I mean, in some instances, but in like when we have barbecue, people just put the QUE and it's still Q as well. So I mean, you could almost take out any letter and you'll end up with the word Q. It's a really, really strange word. All right, so we have the Q, and a Q is an ADT, that only allows for data to be removed from the front and only allows data to be added to the rear. Add data to the rear of the queue, right? The position after the current, but you could only take data away from the front. And once data is taken from the front, all positions in the queue move forward. It's just like the line in the supermarket or the line in the bank. Okay, once somebody is at the front of the line and they get called up by the teller, everybody takes 1 step forward. And so the line, everybody moves forward in the line. Okay, we use 2 operations to add and remove data from a queue. We have enqueue. Enqueue adds data to a queue. And dequeue would remove data from the queue. Dequeue would take data out. So let's take a look at the enqueue operation. Okay, so I'm gonna copy my queue here. That's in front here. Let's take a look at doing some enqueue operations. So let's say, for instance, I want to enqueue 3 values. Enqueue 20, enqueue 200, and enqueue right? 125. We want to add 3 values to this Q, right? We want to add 3 values to this Q. So what do we want to do? We want to, when we say NQ20, we take the value of 20 and we put it to the front of the Q. And what would happen is that the rear of the Q is going to move up by 1. So this front and rear is now the same value. If we NQ 200, then we have the value of 200 being added here, and rear will move up to this value here. If we have NQ 125, we add 125 here, and the rear will move up to this value here. So we can add we always add, to the end of the Q. We will always add to the end of the Q. Simple enough. Yes? Anybody have any questions about it so far? Mm-hmm. No. All right. Okay. So now, go ahead.
The rear and the front does start at -1.
No, the front starts at 0. In a regular Q, the front will always be 0. Okay, but in a regular Q, the rear will start at -1.
All right.
Okay, because if again you're referencing the positions that exist. If a Q is empty, then it means that the rear of the Q is in a position that does not exist, and the front of the Q holds no data. Okay, and we're going to see how to exploit this just now when we take a look at 2 common values that are common to stacks and queues. Okay, so let's say, for instance, now that we have these values here inside of a queue, and we want to dequeue these values. All right, so we want to dequeue these values. So we have the function enqueue, and the function enqueue would allow us to add a value to a queue. But if we want to dequeue these values, then you are going to have to, and let me just group these. So that I can manipulate them. Right. So if I want to dequeue these values, the dequeue operation removes an element from the front of a queue. So the enqueue added the data to the queue to its rear. And the dequeue operation removes a value from the front of the queue right? It removes a value from the front of the queue, pushing all values up towards the front. So it pushes all values up towards the front. So the dequeue operation is a bit of a pain to write as a function because you're going to have to move them forward, right? We are going to have to say, right, if we have that we want to dequeue values twice, so we call the dequeue function twice dequeue and dequeue. we have value 1 and value 2 is equal to dq and dq. So if we have v1 and v2 as two variables here, when I call this first dq operation, the v1 value will take the value of 20. So the value of 20 is going to come into the v1. The value of 200 will move forward to where this was. The value of 125 will move forward to where this was. When I call the v2 function, the same thing happens. The value of 200 is going to go into the variable v2. The value of 125 will move up. And also, I forgot to move the value of rare. The value of rare will also move along with all of the values. So that the rare signifies where the last position is in the list. Okay? So when it is that we had only moved v1, rare would have been in position 1 because we had 200 and 125 inside of there. What's important to note is that queues are first in, first out structures. So the first value that you placed inside of a queue is the first value that you can retrieve from a queue. Whereas with the stack, the first value that we placed into a stack is the last value that we can take from a stack. Okay? So you might be wondering, where does a stack or a queue come into useful, right, in terms of real life or even applying them to a computer system? Well, a stack is useful in having like the undo, because the thing is, when you press the undo button in a stack, sorry, in a program, you want to undo the last thing done. So because if it is that you write 5 operations, and let's take a look at it in action, right? We have 1, 2, 3, 4, 5. This was the first thing that I wrote, this value of 1. This 5 was the last thing that I wrote. But if I press undo, the last thing that I did is the first thing to be removed. The first thing that I did was the last thing to be removed. So again, the 5 was the most recent. That's the first to go. The 4, then the 3, then the 2, then the 1. Are you all with me? That's where a stack is useful. A queue is useful for things like a print job. Right? When you want it to print in the order that it was sent to the, okay? Because think about a network printer where you have people who, sending things to the printer at all different times. You don't want other people's stuff printing before your stuff. So it's important that we get it in that line. That first thing, the first person to send the job to the printer is the first print job that will be done. Are you with me? Okay, good. See, couple of thumbs up, etc. So one more thing to note is that there are some common functions between stacks and queues. Common functions between stacks and queues. And it's important to note that stacks and queues they don't have to be, but when they are implemented via arrays, they can be finite in value. So what does this mean? It means that a stack could get filled, a queue could get filled, okay? And if it is that a queue gets full, then we have to know whether or not there's space for more data to be placed into this queue, and the same for a stack. If it is that a stack is empty or a queue is empty, then we have to know that, well, because we might be asking for data from the stack or we might be asking for data from the queue, and we cannot return any value because there is no value to return. Are you with me?
Yes, sir.
Okay, good. So what we can do is that we have two functions that are common between stacks and queues. And the functions are called isFull and isEmpty. And anybody wants to guess what these functions do? Does anybody want to guess what isFull does or what isEmpty does?
I guess I'm figuring out if it's full or not.
Right. Yeah, so isFull returns a value of true if the stack slash queue is full. And isEmpty does the same. It returns a value of true if the ADT, because I don't want to write over stack and queue, is empty.
Okay, so it's just like a check?
It's just a check, basically, right? And so our stack and queue, we're going to have a max value associated with the stack and queue. So if it is that rare plus 1 is equal to the max value, then your function is full. In the same way, if it is that either top or rare is equal to -1, then your stack is empty because we see that. We spoke about that in the beginning. We said, look here, we had the -1. If it is that the value of your top, right, is -1, if the value of your top is -1, then what does that mean? It means that your stack is empty. If it is that your value is, that means that your stack is, sorry, that your queue is empty. Are you with me?
Yes, sir.
All right, good.
Yes, sir. So this is dynamic memory, or this is
No,
just
this is utilizing arrays.
okay.
If you implement it in dynamic memory, you will have to have a count and max value to be able to say at what point does your stack become full. Okay? Or if it is that you don't do that, then it means that your stack or queue is limited only by the amount of memory that you have in the computer system.
Okay.
Understood?
Yeah.
So let me just again, we just want to finish off with a nice little exercise. Right? We want to finish off with a nice little exercise. So right. So this is using stacks and queues, describe, right, only describe how you can indicate if a word is a palindrome or not. Okay, so you could start off with this with this value, this word being entered into a stack or into a queue, and you can indicate if a word is a palindrome or not. You remember what a palindrome is, right? Example like Anna or Riska. All right, so you could just use common letters alone. You don't have to do any kind of check to make sure that is all capitals or whatever, right? Capitals or common. So Anna or Riska is a palindrome, right? But Hazard a spelling name right?
Yes.
Is
Right.
not a palindrome. How can we use stacks and queues to indicate that something is a palindrome or something is not a palindrome? This is not a program that you are writing. You're just thinking through. Well, if I place the value inside of a stack or a queue, then how can I use that to indicate that something is a palindrome or not? I'm going to give you all 12 minutes to figure this out. Anybody have any questions before I press start?
So you say to discuss is just to come up with an explanation for how to check it, right?
Yes.
Okay.
You're just not writing code or anything, so okay? So we're starting now, okay?
So is that stack on queue or just stack?
Well, no, you can use a stack or queue. If you could do it using only queues, that's fine. But I would say I would tell you that you have to use a stack and a queue. The answer that we're looking for involves a stack and a queue.
Okay, no problem.
All right. So your time is running. Yeah. I'm gonna pause the recording at this point. All right, so we have stacks and queues being used only. We want to describe how we would indicate if a word is a palindrome or not. Okay, so we have Anna, Riska, and Hazard. We identify Anna and Riska are palindromes, Hazard is not. So our solution, right, which I think is very close to what both Alicia and Hazard were kind of talking and describing with us, right? Is that if I had the word, let's take Anna. Okay, if I had the word Anna, I would put Anna both into a stack and into a queue. So if I put Anna into a stack, according to the numbers, I will get A, N, and A into my queue here. And in my stack, I will get A, N, and A. So I have Anna in my stack and I have Anna in my queue. And what I would do then is I would pop and dequeue and compare them and see if the letters match. So when I pop A and A, I get a match. I pop N and N, I get a match. I pop N and N, I get a match. And I pop A and DQ A, sorry, and I get a match. Okay? Let's see how it works for Hazard. If we had the word hazard, Hazard, When I put it in the queue, I have H, A, Z, Z, A, R, D. Well, when I put it in the stack, right? Remember the stack is starts at the bottom and goes up. I have H, A, Z, Z, A, R, D. When I pop and I DQ, I'm first taking out this and I'm first taking out this. They don't match. So right off the bat, I know that I don't have a palindrome. Okay? And again, the same for RESCAR. If I have the word RESCAR, I put into my stack RACECAR, and I put into my queue RACECAR. So once I DQ this and I pop this, they match. Once I DQ this and I pop this, they match. And I keep on doing that until both of the structures are empty. And once they match in that way, then I know that it's a palindrome. Okay? I think maybe Hazard was telling me to do this, but only up to the halfway point, which would be fine. Okay? It would be fine. But then, you know, I'm thinking in the event that a word that starts in the same way that another one finishes, you might have a conflict for a non-palindrome word. But that's something that we could probably look into with a little more testing. Anybody have any questions about the solution? Right. Yeah, Hazard, I realized that that's what you were doing, except you divide the stack in half. Okay, so it's fine. I think that was a fair effort. Okay, all right, Jaden, I understand where you're coming from. No questions otherwise. Anybody else have questions?
Not so good.
All right, no problem. All right, so I guess I will see you all on Wednesday, not physically, online again, right? We've pretty much covered the concepts behind stacks and queues. Now we want to look into the programming of stacks and queues. Okay, and once we get into the programming of stacks and queues, we would have, by the end of this term, covered the greater part of 2 modules, which I think puts us in a really good position to be able to just take time and understand module 3 and also work on our SBA next year. Okay, so y'all are doing well. Just take your time. Take your time, you know, focus on the end of term assignments. I really want you all to do some of the ERD and DFD so that I could possibly use it for extra credit. And that would be it. So if nobody have anything to say again, it is now 11:04. We could end class here.